Hello! It is great to be back with you for another deep dive. I had a bit of a moment this morning. I was sitting in my car waiting for a red light, and I pulled up a video on my phone. It loaded instantly, high definition, no buffering, and I just found myself staring at it for a second, thinking, how?
It really is the closest thing to magic we have in our daily lives, isn't it?
It is. We spend, pretty much every waking second online now. We're streaming movies, sending emails, doom scrolling social media. But if I'm being totally honest, the actual mechanics of it feels like a black box. I tap a piece of glass and information from a server in, I don't know, Sweden. It just appears in my hand.
And usually we only think about it when it breaks, when that little spinning wheel shows up, then we suddenly become very aware of all the infrastructure.
Exactly. So today we are going to ruin the magic trick. We're going to peek behind the curtain at the plumbing of the digital world.
That is the plan. We have a really interesting stack of sources today, primarily focusing on the CompTIA A+ Core 1 and Core 2 material. This is the certification standard for IT professionals, so we aren't just reading blog posts here. We're getting into the real nuts and bolts of network addressing and internet connections.
So this is the stuff the people who actually keep the lights on need to know.
Precisely. We're going to look at how that connection physically enters your building, the hardware that manages the traffic, and the language, the protocols that computers use to actually understand each other.
So the central question we're trying to answer is simple. How does a click on my screen actually travel through wires or, thin air to fetch a video or an email? We're going to decode that alphabet soup of acronyms everyone pretends to understand. TCP, IP, DNS, DHCP.
And hopefully by the end of this, you'll understand why your internet connection might be technically fast, but your streaming video is still buffering.
Okay, let's unpack this. Let's start at the very, very beginning, the physical connection. Before we get into all the invisible data, the internet has to physically get to our house or office. And looking at the sources, it's not just one type of wire anymore, is it?
No, not at all. And this is a case where geography is destiny. The type of physical connection you have available really dictates the speed and reliability you can expect. The sources lay out the most common Internet Service Provider, or ISP, offerings. The first one, which you probably have right now, is cable internet.
Is that the same wire that brings in cable TV?
It is. It uses those coaxial cables with the little screw-on F-type connectors. Because the infrastructure was already buried in the ground for television decades ago, it just became the easiest way to roll out broadband.
And it's usually pretty fast, right?
Generally, yes. But the sources point out a specific quirk with cable. It's often a shared medium at the neighborhood level.
Shared. What do you mean, like I'm sharing my connection with my neighbors?
In a way, you share bandwidth at a local node. So if everyone on your street gets home at 6:00 p.m. and starts streaming 4K movies at the same time,
I might see a speed dip.
you might. It's like water pressure in an apartment building. If everyone turns on the shower at once, the flow slows down.
That explains a lot about my Tuesday evenings. Okay, so that's cable. But then there's DSL. I feel like DSL is becoming a bit of a relic.
It is, but it's still widely used, especially in areas where cable or fiber hasn't reached yet. DSL stands for Digital Subscriber Line. It uses the legacy copper telephone lines.
The old phone lines.
Right, the plain old telephone system, or PSTN.
And isn't there a major limitation with DSL? Something about distance.
There is, and it's a physics problem. It's called attenuation. With DSL, your speed degrades significantly the further you are from the ISP's central switching office.
Why does that happen?
Because you're sending high-frequency data over old copper wires that were designed for analog voice. The signal just gets weaker and weaker over distance. Think of it like shouting to someone across a football field. If they're 10 feet away, the message is clear. If they're at the other end zone, you're going to lose a lot of the detail.
So my neighbor down the street could literally have better internet than me just because they're 1,000 feet closer to the phone company's building.
Absolutely.
That is wild. Okay, let's talk about the one everyone wants. The gold standard. Fiber.
Fiber optic. Yeah, this changes the game completely. Instead of sending electricity over copper wires, we're sending pulses of light through tiny strands of glass or plastic.
And light is just faster?
It's not just about the raw speed, it's about signal integrity. Fiber uses something called total internal reflection. The light basically bounces down the inside of the glass tube without leaking out, which means it can travel massive distances without losing signal strength.
And it doesn't have the same interference issues as copper?
No, and that's the other huge advantage. It's immune to electromagnetic interference. You could run a fiber line right next to a high-voltage power plant, and the signal wouldn't flicker. Copper would be a total mess in that environment.
But here's where the sources get really specific, and I think this is where people get tricked by marketing. They distinguish between fiber to the curb and fiber to the premises.
This is such a crucial distinction.
What's the actual difference?
So fiber to the curb, or FTTC, means the ISP runs that high-speed fiber cable to a gray utility cabinet on your street corner. But the last leg, the connection from that cabinet to your actual house, they use the existing copper telephone or coaxial wires.
So you have a race car engine, but you're putting bicycle tires on it for the last mile.
That is a perfect analogy. You're completely bottlenecking the speed at the very end. Whereas fiber to the premises, or FTTP, runs that glass strand all the way through your wall and plugs directly into your equipment. That's the only way to get those true gigabit speeds, both up and down.
So if I see a flyer for fiber internet, I really need to read the fine print to see if it's coming to my house or just to my street.
Always check the fine print.
Now, we have to talk about people who can't get wires. Rural areas, remote locations. The sources discuss satellite internet.
Right. And for a long time, this was the only option for a lot of people off the grid. Traditional satellite uses geostationary satellites. They sit about 22,000 miles out in space to match the Earth's rotation.
That sounds incredibly high up.
It is. And that creates a massive problem called latency. Even moving at the speed of light, the signal has to travel 22,000 miles up and 22,000 miles back down. That creates a noticeable delay.
So you click a link and you wait.
You wait. It's fine for email, but it makes things like Zoom calls or online gaming almost impossible because of that lag.
But the sources mention a new type of satellite, like Starlink.
Yes, low Earth orbit, or LEO systems. These satellites fly much, much lower, hundreds of miles instead of thousands. Because that round trip is so much shorter, the latency is drastically reduced. It's making high-speed, responsive internet accessible in places that never had a chance before.
And finally, there's cellular. We all have it on our phones, but 5G is supposedly changing the home internet game too. Is it just faster 4G?
It is faster, but the technology is fundamentally different. The sources highlight something called massive MIMO.
Massive what?
MIMO. M-I-M-O. Multiple input, multiple output. Think of a 4G tower, like a floodlight. It just bathes the whole area in a signal. A 5G tower with massive MIMO is more like a whole bunch of spotlights. It uses dozens of small antennas to shoot directed beams of data to specific devices.
That sounds way more efficient.
It allows for massive data density, which is why 5G is actually becoming a viable alternative to cable or fiber for home internet. You just put a receiver in your window, catch the beam, and you're online.
Okay, so we've got the signal to the building. Now we have to deal with the hardware inside. And this is where I think a lot of people, myself included, get confused. There's usually a box in the closet or under a desk with blinking lights. Is it a modem? Is it a router? Is it both?
That is the most common confusion in home networking. And to be fair, in most homes today, it is both, physically. But they perform two very different jobs.
Okay, let's break them down. What is the modem actually doing?
Think of the modem as the translator. That's its whole job. The signal coming from the street, whether it's light pulses from fiber or radio frequencies from cable, your computer can't understand that native signal. It only speaks digital, ones and zeros.
So the modem stands at the door and just converts the language?
Exactly. It modulates the outgoing digital data into a signal the wire can carry, and then it de-modulates the incoming signal back into digital data.
Modem.
I honestly never put that together. Modem. Okay, so the modem gets the data in the door, then what does the router do? The router is the traffic director. Its main job is to forward data packets between different networks. Specifically, it connects your local area network, your LAN, all your home devices, to the wide area network, the WAN, which is the internet.
So the modem brings the mail to the building, and the router sorts it into the different mailboxes for each device.
That's a great way to put it. It ensures the Netflix movie goes to the TV and the email goes to your laptop, not the other way around.
The sources also list a few other pieces of hardware switches and access points. Where do they fit in?
A switch is basically a digital power strip for Ethernet. You plug cables into it to connect multiple computers together in a wired network, and an access point, or AP, is the thing that actually creates the Wi-Fi signal.
But I don't usually go to the store and buy a switch and access point separately.
In a big office, you would. But in a Soho setup, that's small office, home office, we typically use a wireless router. And that's really a 4-in-1 device. It's a router, a switch, a wireless access point, and usually a firewall, all crammed into one plastic box.
Since you mentioned firewalls, that's the security guard, right?
Yes. It filters traffic, it looks at an access control list, an ACL, to decide what's allowed in and what's denied. It protects your local network from unauthorized access from the outside world.
So we're plugged in, the hardware is humming, now the computers need to actually talk. This brings us to the language of the internet. The sources spend a lot of time on the TCP/IP model.
This is the absolute framework for all internet communication. The Transmission Control Protocol Internet Protocol Suite. The source material breaks it down into 4 layers, and understanding this is the key to understanding how data actually moves.
Okay, let's walk through the life of a piece of data, say an email I'm sending. It starts at the top layer, right?
Correct. The top is the application layer. This is where you, the user, live. Your web browser, your email client using protocols like HTTP or SMTP. This is the interface.
Okay, I hit send. What happens next?
It goes down to the transport layer. This layer handles the logistics. It breaks your email into small chunks called segments and decides how to ship them. And this is where we see that famous duo, TCP and UDP.
We'll come back to those because that's a big topic. What's layer 3?
The internet layer. This is all about addressing. The system takes those segments and wraps them in an envelope with an address on it, the IP address. It figures out the best path for the data to take across the world.
And the bottom layer?
The link or network interface layer. This is the physical transmission. The digital envelope gets turned into electrical pulses on an Ethernet cable or radio waves in the air to physically move to the next router in the chain.
So when I send an email, it gets wrapped up layer by layer, encapsulated travels across the world, and then gets unwrapped layer by layer on the other side.
Precisely.
Now let's go back to that transport layer. You mentioned TCP and UDP. The sources call this the Great Debate. What is the actual difference between them?
Think of it in terms of reliability versus speed. TCP, the Transmission Control Protocol, is the perfectionist. It is connection-oriented.
What does connection-oriented mean here?
It means before it sends any data, it sets up a formal connection. It does this 3-way handshake. Your computer sends a SYN message, synchronize. The server replies with SYN ACK, acknowledging and synchronizing. Your computer replies ACK, acknowledge.
That sounds very polite, very formal.
It is. And only then does data start to move. And if a packet gets lost along the way, TCP notices and resends it. It guarantees the data arrives perfectly and in the correct order.
So I'd use this for things that must be accurate.
Exactly. Web browsing, email, downloading a file. You don't want half an email or a corrupt banking transaction.
Okay, so then what is UDP?
UDP is the User Datagram Protocol. It's connectionless. We call it best effort.
Mm-hmm.
Imagine you're just throwing letters out of a moving car toward a house. Some might make it into the mailbox. Some might land on the lawn. You don't stop to check.
That sounds bad. Why would we ever use that?
Speed. TCP has a lot of overhead. All that handshaking and error checking takes time. UDP has very little overhead. We use it for things where live is more important than perfect.
Like streaming video.
Exactly. Or voice over IP calls or online gaming.
Ah, I see. So if I'm playing a game and one single packet gets lost, my character might just glitch for a millisecond, but the game keeps going.
Precisely. If you use TCP for a live video call, every time a packet was lost, the video would freeze completely until that packet was resent. With UDP, it just glitches for a split second and moves on. You'd rather have a glitchy stream than a frozen one.
That makes total sense.
Right.
Now let's talk addresses. We mentioned the internet layer uses IP addresses. The sources highlight a pretty massive crisis involving IPv4.
Yeah, the address crisis. IPv4 is the system we've used since the early days of the internet. It uses 32-bit addresses, using the 4 numbers separated by dots, like 192.168.1.1.
And if you do the math on 32 bits.
You get about 4.3 billion unique addresses.
But there are way more than 4.3 billion devices on Earth. I mean, between phones, laptops, watches, smart fridges.
Oh, yeah. We technically ran out of IPv4 addresses years ago.
So how are we still online right now? Why didn't the internet just stop accepting new devices?
Because of a very clever workaround called NAT Network Address Translation. This is something your router does.
How does that solve the shortage?
Well, think of a massive corporate office building. The building has one street address, that's your public IP address. But inside the building, every single desk has an extension number. Those extensions only work inside the building. You can't call them from the outside.
Okay, follow that.
NAT does exactly that. Your ISP gives your router one public IP address. But inside your home, your router gives your phone, your laptop, and your smart TV private IP addresses. These usually look like 192.168.x.x or 10.x.x.
So the outside world only ever sees the router.
Correct. The router takes your request, slaps its own return address on it, sends it out, and when the reply comes back, it remembers which device inside the house asked for it and forwards it along. This allows us to hide billions of devices behind a much smaller number of public addresses.
That is a brilliant patch. But what's the permanent fix?
The permanent fix is IPv6. This is the successor. Instead of 32-bit, it uses 128-bit addresses. They look totally different. Hexadecimal numbers separated by colons.
And how many addresses does that give us? Is it just 4 times as many?
Oh no, it's exponential. It's 340 undecillion addresses.
I don't even know how to visualize that number.
Think of it this way. We could assign a unique IP address to every single grain of sand on Earth, and we would still have enough left over to give addresses to every grain of sand on a billion other Earths.
Wow. So with IPv6, every device can have its own public address. No more sharing.
Yes. We don't need NAT anymore. It actually simplifies the network and comes with built-in security features like IPsec.
So we have the wiring, the hardware, the language, and the addresses. Finally, we have the helpers, the services that make all this usable for us humans.
Right. Because you don't want to be typing in IP addresses manually all day.
No. So first up is DHCP. The sources call this the concierge.
DHCP stands for Dynamic Host Configuration Protocol. When you walk into a coffee shop and open your laptop, you don't have to manually configure your network settings. You just connect. DHCP is what happens in the background.
It's a conversation between my laptop and the network.
Yes, it's the DORA process.
Yeah.
Discover. Your computer connects and basically shouts, "Is there a DHCP server here?"
Right.
Offer. The server hears that and says, "Yes, here is an IP address you can use. Request." Your computer says, "Great, I'll take it." Acknowledge. And the server says, "It's yours."
And that all happens in a split second. But here's a really practical detail from the source material. What happens if DHCP fails? Like, if the server is down?
This is a huge troubleshooting tip. If you've ever seen your computer say limited connectivity, or you check your IP and it starts with 169.254, that is an API-PA address, automatic private IP addressing.
And what does seeing a 169.254 number actually tell me?
It tells you that your computer shouted for a DHCP server, nobody answered, so it just gave up and assigned itself a random number from that special range.
And I can't get on the internet with that.
No. You can talk to other devices on your local link, maybe, but you cannot reach the internet. So if you see 169.254, you know your problem isn't the cable or the website. It's that your computer can't find the DHCP server.
That is the kind of detail that saves you hours of frustration. Okay, next helper, DNS.
The domain name system. This is the phone book of the internet. Computers don't know what Google.com is. They only understand IP addresses.
So when I type a URL into my browser,
Your computer asks a DNS server, usually on port 53, what is the IP address for Google.com? The server replies with the numbers, and then your computer makes a connection. Without DNS, we'd all have to memorize long strings of numbers to visit websites.
you mentioned port 53 there. The sources have a list of common ports. I like to think of these as apartment numbers at the IP address.
That's a perfect way to view it. The IP gets you to the building, which is the server, but the port number gets you to the specific service running inside that building.
Let's do a quick rapid fire on these so people know what to look for. Web browsing.
Standard web traffic HTTP is port 80. If it's secure, encrypted web browsing HTTPS that uses port 443.
Okay. Email.
A few. SMTP for sending email is usually port 25. For receiving email, we use either POP3 on port 110 or IMP on port 143.
File transfers.
That's FTP. It actually uses 2 ports, 20 and 21.
And what about remote access, like when I call IT support and they take over my mouse?
That's usually RDP Remote Desktop Protocol on port 3389.
It really is a system where everything has its designated place, its own little door.
It absolutely has to be. Standardization is the only way different machines from different manufacturers built in different decades can all work together seamlessly.
So when we zoom out, what does this all mean? It is kind of mind-blowing.
It is. Think about that single email you send. It starts as the thought in your head. You type it into an application. It gets chopped up into segments by TCP, addressed by IP, translated by a modem into light, shot through a fiber optic cable under the ocean, routed by a dozen different routers, and it all happens in milliseconds.
And we get annoyed if it takes 3 seconds.
Exactly. We are incredibly spoiled by the engineering.
But the practical takeaway here, and what the CompTIA material really emphasizes, is troubleshooting. It's not just trivia.
Right. If you understand these layers, you can actually fix the problem. If you can ping a website by its IP address, like 8.8.8.8, but not by its name, you know your internet connection is fine, but your DNS is broken. If you get that 169.254 address, you know your DHCP is down. If you have a blinking light on the modem, it's probably a physical layer issue.
You stop just guessing and you start diagnosing.
Precisely. You aren't just rebooting and praying anymore.
I love that. Well, that wraps up our deep dive into the plumbing of the internet. Before we go, what is the one thing sticking with you from this stack?
You know, it's the IPv6 transition we talked about. We discussed how IPv4 ran out of addresses years ago. We're using this NAT workaround. IPv6 has been available for a long, long time. It's better, it's faster, it's more secure, and it offers basically infinite space. Yet the migration is incredibly slow. We're still clinging to this crowded legacy IPv4 system because it's good enough and changing infrastructure is hard. It just makes you wonder, what other better technologies are we ignoring just because the old broken one is still technically functioning?
That is a great question to leave us with. Why fix it if it ain't broke, even if it is kind of broke? Thank you so much for breaking this down for us.
My pleasure.
And thank you to everyone listening. Next time your video buffers, don't get mad. Just remember the miracle that it's playing at all. We'll see you on the next deep dive.